Briefly, the things I've handed out here to you. The first was your graded problem set number 1. I was generally very satisfied and pleased with the way the problems were written up. Few of you had apparently didn't know quite how to finish problem 2 of that set. So I'm assigning another problem, which is problem set number 3, of which I'll ask you to turn it in Thursday morning, give you 2 days. And the problem number 1 of that set is quite simple, simply an application of calculating partial pressures and compositions of a liquid and vapor phase at equilibrium for a simple system which we assume to be an ideal solution. Ethyl alcohol, methyl alcohol is said to form a solution which is nearly ideal. So in other words, in order to calculate the problem requirements there, one makes the assumption that Raoult's law applies to the liquid phase. And of course, Dalton's law of partial pressures pertains to the vapor phase. Now, this particular problem is an example of calculating what the pressure of each would be and also the total pressure of the system at 20 degrees centigrade. Most of the times we're talking about temperatures up near the boiling point, but this would be will give you some total pressure of this system at some temperature which would be considerably lower than the boiling point of the system at atmospheric pressure. But we can consider a system at some other pressure than atmospheric, and that's what this will turn out to be. So that's very simple. I don't think it takes very many more than a few minutes to work that. Now, problem 2 is a little bit more involved, and involves the utilization of the relationships on the second page of that handout. A procedure for calculating the vapor-liquid equilibrium for ideal solutions from vapor pressure data. Now, you notice on the problem here, I have given you the vapor pressures in millimeters of mercury for pure ethyl alcohol and water over a range of temperatures which spans the boiling points of the 2 components at 1 atmosphere pressure, namely 78.32 degrees centigrade for ethyl alcohol, where you see the vapor pressure is 760 millimeters, or 1 atmosphere, and increasing down to 100 degrees centigrade, which of course gives a vapor pressure of water of 760 millimeters of mercury. The vapor pressure of ethyl alcohol at 100 degrees is 1694, according to this table. So the requirement here is to calculate the vapor-liquid equilibrium concentration for ethyl alcohol and water mixtures, making the assumption that that's an ideal mixture in each case. That is, Raoult's law applies. So you see this. So you see how you combine Raoult's law and Dalton's law of partial pressures to come up with an expression down at the bottom of this little handwritten sheet, where you have an expression for x sub a is is equal to the total pressure of the system minus the pressure of component B in the pure state divided by the difference between the vapor pressures of component A and component B in the pure state. And that's corresponding expression for Y sub A. Now, in order to complete the requirements for this problem, you have to work those expressions for each case here, or at least enough cases for each, let's say, for each temperature, or for any temperature which you know the vapor pressure of ethyl alcohol and water respectively. And I've given you several values here, sufficient number of values, and so you actually work it then for each one. So I'd suggest that your solution should be in a tabular form where you have these temperatures here, and you can copy those or not in the table. Then you'll have a column of X sub A and a column of Y sub A. Or you might want to write columns of some of these vapor pressure difference terms, but anyway, that's in essence is what you get. Now, part B, to plot the values obtained on a graph of true or experimentally determined values and compare, you can use the handout I had last time, which is the observed or the real vapor-liquid equilibrium curve for ethyl alcohol water on a mole basis. Remember, I gave that last time. And so you can plot your calculated values here on that same graph, and then the comparison will be apparent or obvious. And with that, then, it should be simple enough to answer part C of the problem. Well, if there are no questions, here's a question. Yeah.
X of A and Y of A, do they represent the concentration of ethyl alcohol or water?
Well, you could apply it either way, but generally speaking, by convention, we consider A as the more volatile component. In this case, it obviously is because vapor pressures are higher for ethyl alcohol than they are for water at any particular temperature. This is merely a convenience and a convention, but it's not wrong to do it the other way around. But if you plotted water against alcohol, I mean plotted percentage of water, you'd have a equilibrium curve that'll be below the diagonal rather than above. Now, secondly, I hand out a little 3-page mimeographed set of references, and I'll mention in connection with that we have now in the department library across the hall here a little reserve shelf in which some of these are on the shelf. And I had my copy here with the ones checked that are on the reserve shelf, and I must have given that out because I don't have it here anymore. But I think I can remember. So you might want to take this and make a little check mark against those that are on reserve. And there's some of the others I could put on reserve if I felt it was necessary. On page 1, reference 2, reference 3, reference 4, I think it's the 3rd edition of the Perry's Chemical Engineering Handbook, and the chapter on distillation. Item 5, is also on reserve. And incidentally, that table I handed out in an earlier period showing conversions of ethyl alcohol and water. A 2-page table was copied from this little manual entitled Industrial Ethyl Alcohol. Item 9 is on this reserve. I guess item 10 is in a reprint or box file there of collected papers, not all of which are on this list here. Then on page 2, reference 12, we had 2 copies of that, but we can't find one of them, so there's one on reserve. Item 17, I guess, is on reserve, also 16. And item 20, there's 2 copies of that. Item 21. And on page 3, the book, item 31, is not on my reserve shelf, but it's on reserve in the library there for course 124. And there's a copy of item 32. And I guess that's all, except to mention that there is a reprint box with certain selected reprints in there that we have occasion to call your attention to later on. All right, now, last period, and period before that, I guess, we were talking about the various types or behaviors of binary mixtures, binary systems, and we had mentioned that there are three types of binary systems. First of which we call one we can refer to as a normal system, one which the components are soluble in all proportions, or as we say, miscible in all proportions, or mutually soluble. And system forms no azeotrope or constant boiling mixture. Then we have many cases of what we call constant boiling mixtures or azeotropic systems. Or what we call, I could have used the word forms of homogeneous azeotrope. Which is a result of the fact that the system, the components are also mutually soluble in all proportions. And thirdly, we have the system that forms a heterogeneous azeotrope, which is the result of the fact that the components are only partially miscible or partially soluble. And so the word heterogeneous here means that there are two phases, two liquid phases. When you, if you distill a mixture of proper proportions or certain proportions, the distillate has two phases, which are in equilibrium with each other. But that's the reason we call it a heterogeneous azeotrope. And the little handout I gave you was does not give examples of all of these, but I didn't consider that necessary, but rather the first 2 pages of that handout gives an example of our third system here, or an example of a system that displays a heterogeneous azeotrope, namely the system isobutyl alcohol and water. So I'll say a few words about that handout then in front of you. The first page of that is the boiling point composition diagram, in which the overall composition expressed as isobutyl alcohol is plotted on the horizontal phase, horizontal axis, versus temperature on the vertical axis. And you see over on the left-hand corner, of course, the boiling point of water at 100 degrees centigrade. And on the extreme right-hand side, the boiling point of isobutyl alcohol is about 108 degrees centigrade. But if you add a small amount of isobutyl alcohol to water, the boiling point quickly drops. So when you've added about 4 or 5 mole percent of isobutyl alcohol, the temperature's dropped to about 90 degrees centigrade. And if you add add increasing amounts of isobutyl alcohol, the boiling point does not change over quite a range here of composition, where the line is straight across horizontally, the boiling point. Then after you pass about 55% or 50%, I guess it is, we're into the region now in which we have water dissolving isobutyl alcohol, so now you have one liquid phase again. So the boiling point curve rises gradually up to 108 degrees. Then the upper line of that diagram, of course, is the vapor composition curve in equilibrium with the various mixtures. And you can see that if you start out with about let's say 1 mole percent, the boiling point would be around 93 degrees centigrade. And reading horizontally across, you'd see the composition of the vapor would be around 22 mole percent isobutyl alcohol. And if you go back and increase the composition of isobutyl alcohol till you get up to about 4.5, 5 mole percent, then the composition of the vapor has increased to about 33 mole percent. And if you overall system and if you add more isobutyl alcohol, the composition of the vapor remains the same. Because if you add more isobutyl alcohol to the water, you're simply increasing the amount of the other phase. You have 2 phases present now. The little solubility lines are not drawn down here, but they could have been. But I didn't have exact data for the lines over here, which would represent the solubility limits of isobutyl alcohol in water down here at lower temperatures, and over here water and isobutyl alcohol, but they would exist if they were plotted here. So this is an example of the boiling point composition diagram for a heterogeneous azeotrope. In this region where there's a straight line here, which is not exact, it's not, the demarcation line on the right is not too sharp here when the two phases appear, but this represents a region of two liquid phases. Now, what I wanted to call your attention to looking at this is that for systems such as this, when you have very low percentages of a solvent like, or of a solute like isobutyl alcohol in water, let's say less than 1%, which is a situation that we frequently meet up with or have occasion to consider in our systems, practical systems of alcohol water systems. You can see that the composition of vapor is greatly enhanced from that of the liquid. In other words, something around 1% might give you as much as about 20% in the vapor. Well, I'll have more to say about that in a moment, but turn to the second page of that handout is a plot of the equilibrium curve, or the XY relationship, where we plotted the mole percent isobutyl alcohol in the liquid phase on the horizontal scale and in the vapor phase on the vertical scale. So here you can see again that at very low percentages of isobutyl alcohol in water, you have a very great enhancement of the volatility. Much more volatile than water. And then this region of essentially straight line across here represents the region of the heterogeneous azeotrope till you get up to around roughly 50% isobutyl alcohol. And then the curve goes up, but it's below the diagonal line, so that means that above about 33% alcohol, isobutyl alcohol, the volatility of isobutyl alcohol is less than water. Whenever the curve is below the diagonal, it means the volatility is less than the other component of the system. So this is typical of this system exhibiting heterogeneous azeotropes. I didn't hand out to you, but I have also plotted the same system on a weight basis. You can plot these on a weight basis as well. Since the molecular weight of isobutyl alcohol is considerably higher than that of water, it makes the volatility somewhat more impressive. Here, for example, is the vapor-liquid equilibrium curve on a weight percent basis. So here you see at very low values of isobutyl alcohol in water, you have a very great enhancement of the volatility on a weight basis. Here about 2% gives around 40% in the vapor, and so on. This type of plot is entirely comparable, but on a different scale, different basis, of course. Also, I didn't hand this out, but here, to further elaborate upon how we make use of this, is a plot here of isobutyl alcohol, ethyl alcohol system. Actually, this is percent ethyl alcohol and isobutyl alcohol. And you see this forms a smooth curve showing no azeotrope, so it forms a normal system. And it shows that ethyl alcohol is more volatile than isobutyl alcohol in all proportions, as long as you just have pure ethyl alcohol and pure isobutyl alcohol. If we plotted percent of isobutyl alcohol, of course, the curve would be below the axis instead of above. So what does this mean then? Anticipating on a little later discussion, but this means then that we can predict, at least qualitatively, the behavior of isoamyl alcohol in a distilling column. If you'll accept that in a distilling column, distilling alcohol-water mixtures, that we have a concentration of ethyl alcohol from essentially 0 down to the base of the column up to some value which may be 95% alcohol at the top. That very likely isobutyl alcohol, when it's in the if it can be gotten into the region of 95% alcohol, is much less volatile. So in other words, it would be forced downward in the column, in the region of high ethyl alcohol. But in the region, in the stripping column and in the region of the feed plate, a continuous distillation column, it would be much more volatile than water. So it's distilled upward. So obviously at some point intermediate there's going to be a balance where it's no longer more volatile, has an increase in concentration in the vapor phase over that of the liquid, or it have a volatility of 1, we say. And so the third chart on this handout is a little plot of the volatility of certain alcohols, and the volatility is a term we simply use for the concentration in the vapor phase divided by the concentration in the liquid phase under equilibrium conditions, represented here by y over x using our symbols. On the vertical scale, this is plotted logarithmically. These are log scales. And here's percent ethyl alcohol in water plotted on the horizontal scale. Now the values used to plot these curves represent the volatility of low amounts of the particular alcohols concerned. Usually, I think this data was based on concentrations in the liquid phase of about 3/500ths of 1%, or in other words, less than 1%. So that the amount of isoamyl alcohol, for example, that was added when this system was studied to plot this curve was perhaps around 0.5% isoamyl alcohol. Then the system was put into an equilibrium still, which I'll talk about a little more later, and experimentally determined the composition of the vapor that was in equilibrium with the liquid. And then these values were plotted as a function of ethyl alcohol and water. So you see, this is a rather interesting set of curves here from the standpoint of knowing what, or predicting what the behavior of these alcohols would be during distillation in a continuous fractional distillation system, for example. And note that, first of all, I point out that there is a curve here, a little bit heavier line than the others, marked ethyl alcohol. You can plot the volatility of ethyl alcohol as a function of the percent ethyl alcohol in water, and it shows that in very dilute solution of ethyl alcohol in water that has a volatility of about 11:1. I think it's 10.8 is the figure that was used in plotting that value, that curve here, the extreme left-hand side of the ethyl alcohol curve. And of course, at different values, you can take the data off and plot it, and this would naturally decline down to a value of 1 when they have the azeotrope at about 95% by volume, 97% by volume. the value of ethyl alcohol comes down to a value of 1, representing the azeotrope. So then, referring back again to isoamyl alcohol, you see that if we had isoamyl alcohol in dilute solution in a high ethyl alcohol mixture, it would have a very low volatility, only of the order of about 0.2%, 0.2 Y over X. In other words, only about 0.2 as much in the vapor equilibrium as there is in the liquid phase. But it has a steep gradient here. As we decrease the ethyl alcohol content, we have some value, we find a value here at around about 40%, maybe a little bit less, in which it crosses the ethyl alcohol curve. And so at that point, they would have, under equilibrium conditions, the same volatility. And so this is roughly the point at which isoamyl alcohol would concentrate in the distilling column under completely equilibrium conditions. And so the other alcohols represented there can be traced in a similar fashion. Isobutyl alcohol is somewhat more volatile than isoamyl alcohol in high concentrations, but it behaves a similar pattern, except its volatility is slightly less than isoamyl alcohol in very dilute solution, that is essentially in water. And so, similarly for the propyl alcohols, and then I might say a word about methyl alcohol, since we have the chart here. Methyl alcohol, as you probably already know, is lower in the homology series and has a boiling point of about 64.7, as I recall, around 65 degrees centigrade. So in the presence of ethyl alcohol, which would be the right-hand side of this chart, its volatility is higher. And so it's above the ethyl alcohol curve. But similarly, if you have a dilute solution of methyl alcohol and ethyl alcohol water mixtures, its volatility in very dilute alcohol mixtures is less than ethyl alcohol. Something about 6.8 according to this chart here. Three or 4 years ago, I was distilling some pear mash in a pot still, and without rectifying column. Simple distillation. And as we conducted the distillation throughout, we collected in periodic fractions and later analyzed them for methyl alcohol, among other things. And because in the case of fruit brandies, methyl alcohol is an important consideration, as it happens to be. Well, it appeared to be the data was that we were getting an increase in methyl alcohol as the distillation progressed, as the proof dropped and successive fractions were collected. They appeared to be increasing slightly on an absolute basis, but when you expressed the methyl alcohol content of these fractions in terms of the ethyl alcohol present, it clearly was going up. And I said, well, that's very strange. It must be that for some reason or other, the heating process, the prolonged boiling, is breaking up something and releasing methanol as the distillation proceeds. Then I happened to think of these charts we had, looked at it, and it explained exactly that's the way it should be. As you conduct a simple pot distillation, the concentration of ethyl alcohol continually decreases toward zero, and so the volatility of methanol decreases as you go this way. And so toward when you're distilling in from very low percentage of ethyl alcohol mixtures, the the methyl alcohol is less volatile than ethanol, so the ratio of the methanol to ethanol would be greater, would increase. So, chart 4 on that is doesn't have as many examples. It's an example of some esters that were measured in the similar program, in which again we plotted the curve for ethyl alcohol as a reference line here, and now we only have 3 esters here, which are not as important except for ethyl acetate as some other esters, but anyway, it shows a general pattern. Ethyl acetate happens to be more volatile than ethyl alcohol at any ethyl alcohol water concentration, as you see, because the line is above. So what would you predict in a continuous fractional distillation system of the fate of ethyl acetate that's contained in the wine that's fed into the system? Where do you think it would go? He says in the heads product, or in other words, the top of the column. Anybody have a different answer? Or disagree? No, that's correct. It concentrates at the greatest level at the top part of the column. So if you're taking off a heads cut, well, the ethyl acetate would be more concentrated in the heads fraction than in the than in a side stream product. As a matter of fact, the heads product taken from a continuous distilling column most often contains larger quantities of ethyl acetate as an impurity than acetaldehyde, because there's more present in the wines. This all depends on the wine, but it depends on how much SO2 is used in the fermenting process. If a large amount of SO2 is used, maybe the aldehydes will be larger, but many times ethyl acetate is the most important from the standpoint of quantity, impurity, and the heads cut from a continuous distilling column. Now, ethyl valerate, or the ethyl ester of normal valeric acid, 5-carbon acid, you see has that pattern we pointed out before, being less volatile than ethyl acetate, less volatile than ethyl alcohol, at very high levels of ethyl alcohol, but crosses the curve and becomes considerably higher, very great in volatility, in dilute solutions of ethyl alcohol. So what would you predict would be the fate of ethyl valerate, if there was any present in wine? In a general sort of an answer. General sort of an answer. Would it accumulate at the top, or in the middle, or maybe go out the bottom with the bottom stream? Hmm?
It might switch from one to the other.
I didn't quite understand, but
It might switch from one to the other as the alcohol concentration changes. As the ethanol concentration changes with
well, I don't quite understand your answer in the fact that we have a change of ethyl alcohol concentration as we go up and down a column. But if we're talking about a continuous fractional distillation system, the concentration on any particular tray stays the same as a function of time. It doesn't change. So, you got an answer to the question? Pardon?
Somewhere in the middle.
Yeah, it accumulates somewhere in the middle tray. Now, not necessarily exactly the same tray as isomethylene alcohol, perhaps, but some tray intermediate in there. That's what this says. Now, I could have brought along a chart which shows some acids, but I didn't bring them along, but I'll just mention one. If we plotted acetic acid, which generally is our most important or abundant acid, on a chart like this, it would have some curve. It was it would be somewhat higher in water, but nevertheless it'd be below the ethyl alcohol curve in all proportions. It would lie somewhere down here, about as far below the ethyl alcohol curve as ethyl acetate is above it, as I recall. What does this mean as far as the fate of acetic acid in the wine that's fed into a continuous distilling column? What will be its fate, assuming it unchanged assuming it's not esterified in the column? It'd go out in the bottoms, right? Exactly. And so, very little acetic acid appears in the distillate, even though you may have high acetic acid in the wine. But it goes out in the bottom stream. An example of the application of this principle, the behavior of acetic acid in water or ethyl alcohol water systems, is a technique we have to use to determine volatile acid or acetic acid in wines. How do we do it? We take a sample and put it in an apparatus, steam distillation apparatus, then pass steam through until we get about 10 times the original, we get amount of distillate about 10 times the original amount of wine sample taken. It's necessary in order to get the acetic acid distilled over. If you only distill off 10 milliliters, you would maybe only have 20% of the acetic acid in the wine in the distillate. As a matter of fact, later on, if I don't forget it, I'll give you a little problem. When we talk about batch distillation, I have the volatility characteristics of acetic acid and ethyl alcohol and water. So we can calculate by an application of the simple batch distillation formulas or method how much distillate you have to make in order to recover, let's say, 99% of the acetic acid. As I remember the answer to a problem, which I'm not sure, it must have been, maybe it was 99.8% recovery, something like that. It requires distilling off about, as I recall, 7 or 8 times the volume of the original sample. So in other words, 10 times is enough to get 99 9/10% or more recovered. Well, there's one more type of behavior that we ought to mention, and it really would be a fourth one here on our little outline, and that would be the behavior of a completely miscible system. Completely immiscible system, I meant to say. Binary system of completely immiscible components. Now, in reality, probably there are none that are just completely immiscible, but we have many examples of which they'd be so weakly soluble, one component in the other, that we can treat it as if there was no solubility at all. And this would produce, in effect, a heterogeneous azeotrope. The composition of which and the boiling point of which we can readily calculate if we know the vapor pressures of the two components as a function of temperature. And so I'd like to go through this. An example of this behavior, which is sometimes called the steam distillation. We probably had this discussed in chemistry at one time. But nevertheless, where's the rest of my notes here? So this is system D here, or as I call it, steam distillation. It could be called steam distillation if one of the components is water. If it's not, it wouldn't be an appropriate term. But anyway, each component is completely insoluble in the other. That's what we assume. Each component is insoluble in the other. So now we can say that if these compounds are completely insoluble in each other, they behave, if they're mixed, for example, with a stir, they behave as if they're present alone under the system. In other words, they behave as two pure components at any particular temperature and exert their vapor pressure. Whereas for soluble systems, we had that the vapor pressure of a component is equal to the composition of the concentration times the partial pressure in the pure state. Or for non-ideal systems, we had the activity coefficient, which we don't have any numeric. We'd have some activity coefficient times x sub a, p sub a. For immiscible systems, we have no concentration, so for immiscible systems, we'd have the partial pressure component A is equal to its pure pressure. It's exerting its pressure that it would have as a pure component. And similarly, the vapor pressure attributed to component B would be equal to its pure vapor pressure. And so, but of course for mixtures of vapors, why it's no different. The Dalton's law of partial pressure still applies. So the total pressure of a system is equal to the partial pressure of the two components in a binary system, as it is in all cases. But in this particular case, it's equal to the sum of these pure vapor pressures. So similarly, as before, then we say that the composition of the vapor phase is simply equal to partial pressure, component A divided by the total pressure. And Y sub B would be equal to P sub B 0 or total P. Or, in other words, if we want to derive the equation for steam distillation, we can do it very simply by saying that Y sub A divided by Y sub B, we take the ratio, and what does this mean? The term Y sub A means the moles of A divided by the total moles of A plus moles of B, divided by moles of component B divided by the total moles again. And since those are common, they cancel out. And so we have Y sub A over Y sub B equal to moles of A divided by moles of B, which of course is equal to mass of A divided by the molecular weight of A divided by the mass of B, component B divided by its molecular weight. And as we said before, y sub A over y sub B is equal to P sub A sub capital P sub B sub 0. So in other words, equating that to this, and if we want to get the mass of A in proportion to the mass of B that would be distilling, we would have that it's equal to the ratio of their vapor pressures of the two components multiplied by the molecular weight of A divided by the molecular weight of B. And I might also point out that you can write it this way, P sub A over total P minus P sub A. Total pressure system is equal to the sum of the two partial pressures, with each of which now represented by our symbol for capital. Now that's the equation that's frequently given in books as representing the principle of steam distillation. Now, I don't know whether I guess I don't have time, but I had an example here which I take some component like normal octanol, and if you want to know so if you want to know, let's say at 1 atmosphere pressure, what the boiling point would be, you simply plot as a function of temperature the vapor pressure, and you will find that let's say you'd have a curve for water, for example, if this is which it has some value, so it'd come up to 100 degrees centigrade at 760 millimeters. This would be water. Actually, it goes up more exponentially than I indicated here. Now, if you took octanol, it has very low vapor pressure, has a boiling point of about 165 centigrade, molecular weight of 130, it has a curve, something like that. This would be N-octanol, like, for example. Now, the total pressure system would be the sum of the two. They'd be that plus this, so we'd have a curve up here that's the total pressure. This would be P equal to the pressure of water plus pressure of the octanol. And you'll see you would find here, if you plot this out, that at some value about 99.3 degrees centigrade, the sum of the vapor pressure of octanol and that of water would be sufficient to make 760 millimeters, or 1 atmosphere. So that would be the boiling point of the immiscible system if you did it out in the open atmospheric condition. And so then you could, so then if you had a table which showed the vapor pressures at 99.3 degrees centigrade and substitute them in here, you'd have the ratio of the mole you'd have the ratio of the moles here, or that other expression that I rubbed out here, the complement expression for the ratio of the masses that distill. Well, let's stop there and.